Okay, so I believe we're live. Hello, hello, welcome. Hello, hello. So here we are, and what we're looking for is sorry, not looking for anything. We're gonna start. Well, I guess we are. We're looking for a solution. We are looking to solve the problem that we were looking at the other day. That's the goal. That's the plan. And I have a solution, actually. I already have one. So it shouldn't be too bad. Although we'll see how long this takes to actually code it, because I think I may run into some issues. I'm not really sure though. I gotta be clever about how I do this. Excuse me. I think it should be fine. Actually, I think it should be fine. I'll figure it out. But there are some details involved which I haven't totally hashed out in my mind. But once I actually get to coding it, it shouldn't be too bad. So here we go. We're looking at. Excuse me. We're looking at wiggle sort 2, problem 324. Given an integer array nums, reorder it such that nums of 0 is less than nums of 1, is greater than nums of 2, which is less than nums of 3, ... Basically, your numbers are paired off into a smaller and a larger number, and then every pair, the consecutive pairs, if you put them next to each other, the larger of the first pair has to be larger than the smaller of the second pair. So it has to be kind of like a wave type of thing. And doesn't have to be an even number of numbers though. It would just be the last number would be a smaller number. If you have an odd number of things, and if you have an even number of things, it would be the sort of the larger part of a pair. So that's basically what they're asking is how do you can you do this efficiently? Can you reorder numbers into and there's possibly multiple answers, and they just guarantee that every input array has at least one valid answer. And you are to rearrange your numbers so that that property holds, that particular kind of type of sort condition, and they want you to do it with a certain degree of efficiency in terms of the time complexity and the space complexity, right? So linear time complexity and constant extra space. So that's the am I speaking too loud? This might be really loud. I'm sorry. I want to get the volume right. Maybe this is too loud. Hello, 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 hello. Okay, so I think this is better. I don't want to be too loud. I don't want to be too loud. Excuse me. So that's the question. Now the solution that I'm thinking of to do, and there was I don't know how many hours of a previous video where I kind of went through my thoughts. My thinking is you could use what's called quick select, which will find if you were to like sort the numbers, and you have like what's called the median number, which is or would be the middle number. That's basically there's an equal number to the left as there are to the right of that number in the sorting. It's sort of right in the middle when you sort it. That would be the median. And you could pick an arbitrary kind of spot and maybe call it like the second element in the sort, what that number would be. That would be sort of what they call it an order statistic. So the median order statistic is sort of like whatever the array is. So if there's 10 elements, the fifth order statistic would be the median. I think that's right. I don't want to make a mistake. Yeah, if we go 1, 2, 3, and so the second order statistic would be the second element in the sorting, and so on. So what quick select does is it will allow you to find that order statistic given some index that you want. So like if I wanted the 8th order statistic, that would be the answer to that would be sorting if you were to sort everything and take the 8th number in the sorted list, that's the 8th order statistic. So what we want now, what quick select does is that it allows us to find an order statistic in linear time, which is faster than sorting it. So sorting it would be n log n time. It's a little bit slower than linear time, which is just O of n. O of n log n is sorting, and O of n is linear, is finding your order, how the amount of time it would take to find the order statistic. Now, the thing about that that's important is that's actually for, there's a couple notes there, but that is, we're basically going to look, it's expected time linear. It's almost certainly going to be linear time, the way that we're going to implement this. And what we want to do is first find the median order statistic, such that it's actually a little bit larger than the median order statistic. It's sort of the next one beyond the median. It's kind of, basically we want to find an order statistic such that all the elements to the right of that value are greater than equal. We're going to partition the set such that all the elements that are going to be put to the right of that are going to be greater than or equal to that number, and all the elements to the left are less than. We're going to run into a problem though when we do this based off of the inputs. It's actually possible where there are duplicate numbers and the median order, excuse me, there's one more detail we're missing. Specifically, we want to roughly split the array in half. So we want, it's going to be n over 2 plus n modulo 2, meaning if it's an odd number, it'll be n over 2 plus 1. If n is odd, if it's n is even, it's just n over 2. We want that many number of elements in the sort of the larger set. In other words, the stuff on the right that's greater than or equal to the median value that we look for, the order statistic value that we look for. We'll call it the mth order statistic that we're looking for. Everything that's greater than or equal to, we want that to be exactly n over 2 plus n modulo 2, where dividing by 2 is integer division. And the reason for this is that we're going to use these values to create pairs. We're going to actually generate this sort by rearranging these elements, knowing that these ones are the smaller one, this is the smaller set, and this is the larger set, and you can just pair them off and kind of go through the list. Now, the problem that we run into, there are a few problems, but one problem we run into doing this first is that if we have duplicate numbers where some of these numbers are equal to each other, so some of the smaller numbers, let's say, so for this case, if we did what we were just describing, the 2's would end up split, they would actually split. 1, 2 would end up in the smaller set, and 1, 2 would end up in the larger set. Now, if you create this pair where 2 and 2 are right next to each other, unfortunately, this doesn't say less than or equal to, it just says less than or greater than, meaning if you put 2 and 2 next to each other, they can't be paired off that way, and you'd get the wrong answer. So what we've got to do, what I've decided we could, what I've realized one possibility is to alleviate this, is to take all of the values in the smaller set that are equal to that median value, that mth order statistic, that I shouldn't call it median value because it's not technically the median, it's similar, it's very close, but it's not exactly. The mth order statistic, all of those values that are equal to that mth order statistic, we want to pair them off before we do any other processing and kind of shove them off to the side on the left side of the array. It doesn't really matter which side, but just pair them off on one side of the array, and then basically perform the same routine I just described on all the elements that are left over, and partition them again, and you do quick select again for that mth order statistic on that smaller portion, partition it again into smaller and larger groups. Now this smaller and larger group, it should be guaranteed that you should actually end up with the same order statistic again, because you paired off these elements, and I was saying this order statistic is almost the median, where you have half the elements on one side and half the elements on the other, an equal number on the left and the right. Well, if you pair them off and remove them, one from the left and one from the right, every pair it's still equal on the left side and the right side of how many numbers are larger, how many numbers are smaller. So actually you really should get the same answer again. However, I'm going to do the partition a second time because it doesn't really cost you very much more in theory, and it also you still want to partition again anyway. It doesn't really cost much to pick the, what is it? Well, I mean, yeah, I don't actually. Let me think about that. Maybe I will think about changing the. Maybe I will think about. Maybe I will think about separate the partition algorithm that I have here, separate it from, make it separate. So there's picking a random pivot, then there's partitioning around that pivot, and then there's using quick select, which uses that partition routine as a subroutine. I could actually separate the partition routine into both the picking the random pivot and then partitioning around that pivot, and from there actually we don't have to pick another random pivot, quite frankly, which would be interesting. Yeah, think about that. Yeah, it may not be necessary. You do have to partition it again, but you don't necessarily need to pick the pivot again. I don't think you do. I don't think so, because yeah, you actually wouldn't touch that mth median value. You wouldn't touch it. And as I said, the same number of elements that are smaller and the same number of elements that are larger, it's going to be the same position. It's going to be the same. It should be the same mth. I think I want to say, like, I don't have a proof, but I think that's the proof. I think it's literally just whatever's left over. It's going to still be what you're looking for, the same value. So actually, you could just move. You actually just partition around that value, and in fact the yeah, well, I guess you do have to be somewhat careful of, like, where do you put all these other smaller values that you're pairing off with larger values. You could end up shifting. Yeah, the shifting things over properly, I think I have to be careful about that, because if you move, if you move that mth order statistic to a different position than when you partition around it, you need to know what that index is. You need to know what that number is, like where it's positioned to do it properly. But anyway, so I mean, I'll figure that out when I'm coding it, I guess. But well, kind of need to move everything. You could. I have to think about that. How do I actually want to move everything around? It really doesn't matter that much where everything goes, quite frankly. The smaller values can just take some position in the smaller set, and the larger values that are being swapped in the smaller set also you can just place those, because you're going to partition again anyway. You basically just have to throw everything to the side. The only issue is if you want to save yourself another quick select routine to find the mth order statistic again, you would want to keep track of where you move the actual statistic, the mth order statistic. Where does it end up? Yeah, you kind of don't really care where you move your values. You can just move them wherever. You just have to move them somewhere. Yeah, I'm just thinking here. I'll think about it some more when I get to it. Well, actually, maybe now. Yeah, I mean, fairly soon. Fairly soon, I'll be thinking about that. Where to put these numbers when you're moving these paired off values in. Unless you have a lot of duplicates, it really shouldn't be that big of an issue, I think. I don't know if you could hit that case where basically everything gets paired off. I don't even know how that would work. What would happen if you did that? What test case where everything in the small, basically that would mean that everything in the smaller set, no, that would mean basically half of the larger set would be paired off with half of the duplicates, which is half of the smaller set. I think that's the furthest it can go, because if you have more than that, then I mean, I guess it could be the whole smaller set could be all equal to that mth order statistic. Like, you don't even have this problem at all if it's even and everything is smaller and everything is larger, right? If there's like half, if it's an even number of elements and the smaller half, they're all equal to each other, and the larger half are all equal to each other, and they're just two different numbers, one larger than the other. And that you don't even have copies of the mth order statistic, because the mth order statistic becomes one of the larger values. So you would need to be in a position where, but the thing is, right, if you have more than, like every smaller number needs to have a larger number associated with it, right, paired off with it. So how many numbers really can you have then that are equal to the mth order statistic, but also falling on the smaller side? I don't know. I want to say it's possible to do half, like half of the array is all 2s, and then 1/4 on the left side is all 1s, and 1/4 on the right side are all 3s, and you could just pair up the 1s and the 2s for a while, and then pair up the 2s and the 3s for, or how'd it go? Yeah, 1, 2 for a while, and then 3, 2 for a while. Like that could work. However, could you go with more 2s than that, right? I don't think so, because, well, if you have more than half of the 2s in the smaller set, well, if you have more than half of the 2s in the whole array, if your mth order statistic is more than half of the whole array, you don't have a solution, right? Because that means that you don't have enough larger values, or you don't have enough smaller values to pair off in either direction. However, you could have like that, where that half of the array is positioned could be moved to the left side a bit. It can move completely to the left side. So, or yeah, I think I guess it's more obvious if it's moved further to the left, because you need to have, well, yeah, as you move it to the left, you need more of these larger values that are larger than the median, the mth order statistic, to pretty much cover those smaller values, to be able to pair them off. But I guess so the largest number of so for the pairing, right? That's the thing. So we want to know, like, how much displacement happens in our array in the worst case with regard to these pairs. So you could move your half of the array almost all the way down to the left side, but still be equal to the mth order statistic. So it's almost half. So basically there's one element on the left side that's not. So you'd have a 1, you'd have, half, if you had 20 elements, you'd have a 1, 20 2s, or excuse me, 10 2s, and then 9 3s. And the 9 3s would end up being paired off with the 9 2s, the first 9 2s, and the last 2 would get paired off with the 1. And yeah, I guess excuse me, I have just 2, 3 pairs all the way down. Excuse me, from left to right for a while. And yeah, you do end up moving where the mth order statistic will be. So you do need to pay attention to, when you're moving the elements, check if it's the index that you're about to move, if that's the index you're currently on, and then update the mth order statistic index with that, so that way you can avoid another call to quick select. And what you'd end up doing, I guess, is you take your 2, you swap it, there's sort of an index for each pair, sort of two slots that you're looking at, and you would say, excuse me, you basically would start from the mth order statistic and move down to the left, and also start with a pointer on the right side of the larger values, right all the way on the right, and you would just take these two values and swap them with whatever is in those positions that you're looking at, and basically through all these swaps, you'll end up pushing values all the way to the right side. I mean, it's a lot simpler to just do another quick select partition on what's left over to find the mth order statistic again. I think that's probably just a lot simpler to do. I think I'd probably just do it that way, because the problem you run into is like now you have to figure out, like, okay, if you're swapping with the mth order statistics, new index or current index. I guess that's actually not that hard to do, because it always has one index, and you just keep updating it as you move it around, and you just have to be careful that whatever you're swapping is not that value. I suppose you do run into another issue where you actually kind of want to. No, you run into another problem too, where you probably want to do it somewhat in bulk, in the sense that you actually can end up overtaking all these twos that you've got going on, all these sort of copies of the mth order statistic, because you're moving every two slots, and you're only moving 1, 2 away, and swapping it with well, actually, I think what it amounts to is you just shift them all down, really. No, I'm just thinking, how do you? How do you do this properly? Like, the first two, you would swap it with the 1. That 1 you would swap with the 3. And then you have the next 2. Right, actually the next 2 is already in the right spot. And then you would swap the 2 that's to the right of it with another 3, we'll say. However, that 2 basically disappeared now. You don't know what happened to it. And I think actually then what's probably prudent is once you get halfway through, you really, yeah, I guess actually you want to do this recursively then, and you actually do want to partition again around the mth order statistic, and what you want to do is move your pairs until you hit a point where I guess you hit like half of the array or something, and or either yeah, because you're going to overtake all of these numbers anyway, so really it's got to be some portion of the array that you've kind of set all these pairs off on the side. Just thinking, how far should you go? Basically, you're going to take care of half of the duplicates in one shot. I would say just keep a count, and count the number of duplicates. I wouldn't even do that. No, forget that. That's just. No, it's. I think you would literally just keep going until you hit one of these values that you moved in. It's not a duplicate anymore. You just go from right to left, shifting these elements into the right spots, shifting the duplicates into the right spots, and shifting the elements from the right side into the right spots. 2s and the 3s really, and then you eventually actually hit a 3. You hit what you just swapped in there, and then you say, okay, now that we've paired all this stuff off, let's take all this stuff on the right side now. It's just everything's been kind of jumbled, and let's just recurse or iterate again. Get the order statistic, check to see if you have any duplicates, and do the same thing again. If you have duplicates on the mth order statistic, and do the same thing again, and just kind of do some pairing off. And I guess you would do half of the elements the first round, then you do the half of that half, and then half of that half, and I guess you would keep going until you basically keep going. You keep iterating that approach until your nth order statistic doesn't have any duplicates on the left side. Then you can use the normal routine where if you knew, basically if you know that everything on the right side is larger than everything on the left side, you can just pair things off straight across and you'll have no issue. And I want to say that's the approach. That's the way to do it. So actually you would have a few quick select iterations and the resulting partitions. And the reason why you would do that is you want to sorry, I'm just thinking actually. I'm wondering why. I believe anyway, I'm just thinking about it. I believe when you quick select onto a certain index, it actually does partition the array appropriately. But that's kind of beside the point. What I'm trying to say is is that right? I don't know. I'm actually not sure. I'm not sure if like quick select actually. I'm kind of assuming that this. Actually, I don't know. I'm thinking now they could prove that, because the way this works as quick select is that we sort of partition a few times and find random pivots until we find the pivot we're looking for. But I don't know that the whole array is, partitioned around that pivot appropriately. The whole section. There's no guarantee of that, actually. Which is interesting. Just thinking, is that even... There's like an assumption, the underlying assumption here that I don't think is necessarily correct. Even though we use quick select for like the median, for instance, it's kind of assumed that everything to the left and everything to the right are going to end up in the right spots, but it's not necessarily true, right? You could have like the pivot here and everything on the left side is smaller, everything on the right side is larger, and then you say, okay, well, you need to find the pivot here now, and let's say you find like something in the middle and everything's partitioned on the left side and the right side. And certainly these, because they're less than this pivot, also would be less than this pivot. And obviously these ones we partitioned, but then we need to go to the left again, and we have this portion. We partition this part, and we say everything to the left of, I guess, I don't know, this part maybe was the previous. We'll just suppose that was the partition before. I think I'm just kind of just jumping around a bunch, so I might not be in the right spot, but everything to the left of that is smaller than this, everything to the right is larger, so for this new one, everything to the right of that is also larger than that, and the numbers in between have to get set properly, and the numbers to the left are obviously less than this, and these ones are less than this, but are these ones less than this one? That's like the question. Like, I think it's possible to end up in a weird spot with this. Certainly these ones are smaller over here, but these elements in between, well, yeah, actually I think it's guaranteed, because every iteration, like, you would have to first iterate on this whole section first, find some value, and then you have to pivot on that. So yeah, I think it's actually, I think it's consistent. I actually do think you don't need to partition again. That's kind of what I'm trying to check. If you need to partition one more time to get things in the right spot. But yeah, I think you, in the case you had like a whole bunch of 2s and a 3, or half, you know, 1, 1, 10 2s and 9 3s. In that case, if you pair off 2 3, when would you end up stopping? If you go, you'd have basically these 9 2s. You'd pair 1, 2, 3. Let me just see. Actually, we can kind of look at this way. 1, 2, 2, 2, 2, 2. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. So how many numbers do we have here? Oh, I shouldn't have done that, but that's okay. 1, 2, 3, 4. Oops. 1, 2, 3, 4, 5, 6. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, that's what we're looking for. So we pair these off, and we have sort of, this one we don't touch. We start here, right? We go 1, 2, 3, and that will put us at 1, 2, 3, 4, 5, 6, and we have 7. And the 7th one, after that, we would, yeah, so we put 7 of these on the left side, or we put a few of these on the left side. We do 1, 2, 3. I don't know if it really matters how many you go through. 1, 2, 3, 4, maybe. 1, 2, 3, 4, 5, 6, 7. And then I think the rest of it would be, and basically we're just swapping 1s and 2s all over the place. I think 1 ends all the way at the end, ends up all the way at the end, and the rest are still 2s and 3s. So we'd have, how many 2s we get? 1, 2, 3, 4. That gives us 5, 6, 7, 8, 9, 10. And then we have 4 less 3s, which is 5 3s. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then here you go, like this. So now you have 1, 2, 3, 4 2s on the left side, and you would have 2, 3, 2, 3, 2, 3, and this 1, 2, 3. This 4th 2 would actually end up here, would be right here. And then when you go the next 2 on the left side of that, or you would really, you wouldn't start here, I'm sorry, you'd start down here. 1, 2, 3, 4. It actually is already in the right spot. Then when you go to the next 4 on the left side, the 3 you look at is just another, the 3 you look at is another 2. Or excuse me, the 3 would be like one of the other 3s that you already swapped. And it kind of doesn't matter. I mean, even if you didn't, if you like somehow like replace the 2 and the 3, you would just end up just swapping a 3 with another 2 with another 3. It really doesn't matter. And yeah, so basically you just keep going to the left until you hit something that's not a 2, and swapping like so, and you would end up with something like this, which we have 1, 2, 3, 4, 5, 6, and then now you would end up partitioning this again into 2, 3, 2, 3, 2, 3, 2, 3, and then you'd have 1. How many 2s are there? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And how many 3s? 1, 2, 3, 4, 5 3s and a 1. Oh, excuse me, the 1 would be, yeah. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Wait a minute. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah, you'd have something like this, and then you'd repeat the same procedure again with the pairing. So you'd have 2, 3, 2, 3. Oops, 2, 3, 2, 3, 2, 3. And now you'd have again 1, 2, 3 2s. So 1, 2, 3, and you really wouldn't get that far. You'd probably get 2 of these, right? You maybe would get, if you get 1, now the 2 is here. If you get the next 2, you get 2, 3. If you get 2 of them, right? 1, 1, 2, and then this third one, it's actually in the right spot already. It's already where it's supposed to be. Let me see. 1, 2, 3, 4, 1, 2. Yeah, this would actually be paired off too, and it would be in the same spot. Oh no, I'm sorry. You wouldn't, no, because you don't start on this one. You actually leave this. So you go the 1, 2. So 1, 2 would put you 1, 2, 3, 4. Yeah. So it's 1, 2. These 2, you would be done, right? So you have 1, 2, 3, 4, 5, 6. You still have 4 2s. 1, 2, 3, 4. And how many 3s we have? 2 less 3s. 1, 2, 3. Right, 1, 2, 3. Less. Yeah, like so. Like so. And so you have this sort of a thing. Now 1, 2, 3, 4, 5, 6. So 6 of these 2s. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. And you would do the same thing again. You partition again. 1, 1, 2, 3, 4. 1, 2, 3. And I'm just thinking, because this is kind of like the worst case. I just want to make sure that this not only does it work, but it also, the runtime isn't too bad. The runtime should still be basically linear time doing it this way, because the partition that you're operating on, the number of elements gets smaller and smaller. You never really perform more than a linear number proportional to the size of the array, which basically once you operate those elements, they're gone, and then now so you do sort of the overall time complexity should still be linear, which is kind of interesting, because you might think that doing this would give you, actually no, this could be quadratic. I'm sorry, this might not be linear anymore. I could be wrong about that. I want to say what you need to guarantee that it's still linear is you need to throw out like some significant proportion of what you're operating on each time. So here it's like, it's not half, but it's sort of like half of these duplicates almost, and then half of what those ones, and then half of those ones. So it's if you take a geometric sum, you end up with a linear number of operations to do this. Yeah, I believe that it still works out, still linear, the calculation, even though we're repeating this a few times. So now you have 1, 2, 3, 4, and 1, 2, 3, and you'd end up with 2, 3, at least 1, right? 1 here, 2, 3. Oh no, I'm sorry, this one. 2, 3 here, this one, and then this next 2 is in the right spot already, right? So you do 2, 3, and this 2, 3, and then you're done. Right after that, it's a 3 again, and then you have a 2, and so you have a 2. The 2 3s were used. You have a 3 and you have a 1, right? Let me see if that's right. It looks like 1, 2 pairs, right? 1, 2. This is stays, and 1, 2, 3, 4. We used 2 3s as a 1. Hold on, 1, 2. There's still 2 2s. Basically, the 2s get kind of thrown over here somewhere. So there's a 2 somewhere over here too. Something like this, where you go 2 3, 2 3. This 2 3. This actually isn't part of the thing. It's just that the 3 happens to be there. Really, this would be the part that gets partitioned again. And so we would end up with, one more time, 2 3, 2 3, 2 3, 2 3, 2 3, 3 2 3 2 3, and this would get partitioned to 1 2 2 3, right? Because this 2 3 is actually not. It just happened to be a 2 3 there. It wasn't part of the intentional kind of rearrangement. So now this 1 2 3 again, there's a duplicate, and so you end up with this whole thing again. 1 2. Okay. We have another duplicate, so that would get paired off with the 3, and you go 2 3, 2 3, and 2 1. Again, this is just kind of what's left over at the end. It's not supposed to be here like this, and you do, right? This 2 gets paired with this 3 over here, and you end up with a 1 over there, and then finally you would partition it one more time. Get the whole thing again, which I probably should just really be copying these. I could do it this way. Oops. Oops. That's a little bit better. So you actually would end up with 1 2 after the partitioning again. And now on the left side of 2, there are no more duplicates. And then you would do the normal routine, which actually would pair off the smaller values with the larger values. Now, the thing that's tricky here is, oh yeah, this is wrong. I mean, at this point, this wouldn't be correct, right? It's a larger value to a smaller value, which then actually should go up to a larger value, which the pairing would this basically is done. Actually, after you partition this, anything that's smaller than 2, even, the only thing I think, the only one you have to work on is 3 or more elements, right? If you have 2 elements, once you partition into the smaller and the larger pieces, the left and the right, then you're done. Excuse me. If obviously there's only 1 element, there's nothing to do. If there's 2 elements, you just have to put the larger one on the right and the smaller one on the left, which the partition will do. And then if you have 3 elements, or the quick select will do, and if you have 3 elements, then you'll have something like 1 1 2, or 1 1 2 3, let's say. You want to have, you're going to end up, you got to put there's a routine where you put every other element is going to be one of the larger values from the larger set, and you can just swap the smaller elements with those larger values. It shouldn't make a difference. And you can go right to left, so you can kind of, it's actually, how does it work? It's there's another way of doing it too. It's simpler. You just kind of set pointers at on A and B. A is the beginning of the smaller elements, B is the beginning of the larger elements, and you kind of increment by 2. And what you're going to do is put what the larger element should be a smaller element, and the smaller element should be a larger element. So you swap them, and you increment by 2, and you keep swapping. You do that all the way across until the pointer kind of goes off the edge of your array, edge of your section of the partition that you're doing that on. That's like the simplest way to do it. Again, the only problem with that is that, as described, if you have these duplicates on the left side of the partition, you need to pair them off appropriately with things that are large enough. And yeah, obviously here we're just going to take things from the back. But otherwise, if you have a regular kind of setup, you can just set 2 pointers and just all the way across. And just thinking if there's, yeah, it's really that simple. It's the mth order statistic is where you set the larger pointer, because that one is the beginning of the larger values. It's actually easier to go backwards, because you can tell at the end, the right side of the partition, if you're odd or even for that partition, you can figure out whether or not you need to end with a smaller number or a larger number. And then you can, so you would say, like, you have this smaller set of the end of, let's say if there's like 6 elements total, there's 3 elements on the left side and 3, or 12 total, 6 on the left side, 6 on the right side. If it's even, you know that ending one should be a large number, so actually you just decrement your pointer by 1. You don't start at the very end, you start at 1 before, and that should be, those are going to be, you're going to loop, those should be smaller numbers every other one from the right side until you cross the mth order statistic, and then you start the other pointer at +1 at larger, right? So those are all smaller on the left side. You want to start the odd ones on the left side, or those are going to get swapped. So then you swap and you move both pointers closer, swap again, swap again, swap again. You just keep doing the swapping until they pass each other, and then you stop. Right after you pass each other, you don't need to keep going, because all of the larger ones on the right side have been swapped appropriately with smaller ones, and all the smaller ones on the left side have been swapped with larger ones. So that's that's pretty simple way to do that. And right, obviously you need at least 3 elements for that to matter. And yeah, if it's odd, you're going to begin at the very last one. If it's even, you'd start at subtract 1 from that. So pretty simple routine, but that relies on everything in the smaller set being smaller than everything in the larger set, which is not true if you have these duplicates that are shared across the smaller and larger sets. So that's kind of the reason for all of this, kind of like, really spending the time to work this out, because there's, wow, it's already almost 50 minutes we spent. Yeah, because it's kind of involved. Like, it's kind of a big deal. Like, it's really, it's a nuisance. And yeah, because each time even though you're doing a linear number of operations at each of these steps, even though you're doing a linear number of operations at each of these steps, if each iteration removes a significant proportion of what's there, which it does, right? It does a half, then a fourth, then an eighth, etc. Then the total number of operations, you could multiply each of those and add them all together by O of n, and you end up with O of n times really just by 1, right? It's a half times a fourth, half plus a fourth plus an eighth, etc. It's a summation of a geometric series, ends up just being a constant, and so it's still linear, even though you're doing sort of iterating over and over. So that's the approach we're going to look to take, and we'll see if it pans out, if it works. We don't actually need to do the separation we were describing before. Also, I had a different algorithm entirely in my mind, but it looks like it doesn't work that way. So it looks like we are going to need to do something kind of special. So, okay. Let's try to figure this out then. So we say we're going to have to do this pair off duplicates, pair off duplicate values. duplicate values of the median are in the smaller set. Left of the median. Iterate until all paired. Okay, try something like this. So, quick select, we do that. We've got things on the right side, things on the left side. We have these median values, median index, median value of that index. And I suppose we could say while, so we'll say int or auto x equals this iterator. So while x is equal to median value, we're going to pair things off. We'll say, I want to say A and B. I'd use, yeah, we could do that. Do it that way. So A is going to be equal to nums.begin, and there's this x, and we say B equals nums.end minus 1, which basically nums.end minus 1. I don't know if we can, or nums.reverse begin. That's I kind of want to do nums.end minus 1. That actually should work. And then we're going to say, while x equals this median value, it minus, really should be it minus 1. We're going to standard swap x. We're going to decrement x with A, and increment A, swap A with B, increment A again, increment, decrement B, and decrement X. Look at that, what a loop. What a loop. And then we're going to iterate again. We're going to partition. Basically going to do this again. And say n equals not num, so we don't need that. Well, yeah, I guess it's going to be what's left over. So now the thing is, I think B is the last thing that we touch, right? Yeah, wherever B is, size minus B, it's going to be sort of end minus B, something like this. I don't know. What do we think about this? Kind of just want to use indices and keep things simple. Yeah, let's do indices. Yeah, I like using, excuse me, I like using iterators. However, indices are fine too. We don't necessarily need to use. Don't necessarily need to use iterators. Excuse me. Okay. So then we have all these pairs, and I guess you could. I mean, there's a few things you could take the nums that are, or whatever n was, and decrement it by. Decrement it by the number of pairs, right? 2 times, and we could figure out the number of pairs, or we could set it to what it was minus b, I think is basically that's the last element. No, it's not b, it's actually a. It's a. So a is the index of sort of the last thing that we swapped with. And it's actually 1 after. So there's sort of 0, 1, 2. A is the index of 2. It's actually the beginning of our new sort of set of elements to look at. And that's actually the beginning of that index. So it's b minus a plus 1 will give you the total number, where b is nums.size, which b is n minus 1. So it's n minus 1 minus a plus 1, which is just n minus a. Yeah, so it's just n minus a is what we want. A little confusing, but that's what we want. And now we want to update this iterator again to, now we're gonna partition again, use quick select again on exactly right, n over 2, n plus n modulo 2, and it's going to be from a to n minus 1, or really it's just nums.size minus 1 again. Yeah, these are the indices you're going to use quick select on, and you're going to update median index to these things, right? And then you're going to do this again. You're going to keep doing this until really this is, put this twice. You'd say you do this once. You do it once up here, and then really do this twice. The double while loop for this condition. So now what's going to happen is oh yeah, okay. You update x again. And right, obviously if there are no duplicates to begin with, then we don't even need to do this. Right, we want to make everything to the left needs to be strictly less than the median value. A and B. B never really changes. B is kind of always the num size. Oh no, we actually update B again to this end piece here. Yeah. Yeah, B we have to set back to where it's supposed to be. And A can be, A actually doesn't change where it is. Yeah, A just keeps going. A just keeps going. So yeah, and we don't really have to worry about things going off the bounds because, like I said, there can only be half of the array are these duplicates. Like the worst case is what we went through before. So A is never going to go off the edge or anything like that. B obviously resets every time at the right side. And we just keep quick selecting over and over. Keep updating n. And we can probably do this, perform this operation, and then finally, now that what the final partition, the array, not the final partition of the array, split two elements that are strictly smaller left of median index and strictly larger than the median value. Can use simple pair. Simple pairing of the elements to complete the solution. It's a mouthful. A lot of explaining. So, int left, int right. We'll start off at left starts off at 1, which is really, it's a plus 1, and right starts off at b. So it's what do we say? It's n plus n minus n plus 1 mod 2, which is to say that if n, it's not even n, it's, yeah, what is n? N is what's, yeah, right, n is sort of the number of elements left over. So if there's 3 elements left over, we want this to be, and b, it's n minus 1. If you're even, so if it's 4 elements, you actually want to move 1 position over. So n plus 1 would be 1. That's if it's even. So you move one element over. If it's odd, n plus 1 would give you 0, and you'd start off at b, which is where you should. Which is a little bit counterintuitive here, I think, that what we're doing there, but that's what we want. So the left and right. Say while left is less than right, we're going to standard swap nums of left, nums of right. And we're going to increment left by 2 and decrement right by 2. And you can actually even, oh yeah, no, we're not multiplying by 2, we're just incrementing and decrementing by 2. And then that should be done. That should be enough. Let's see what compiles here. Oh, minus equals, I'm sorry. Or rather, yeah, minus equals, I forgot the, I looked at it before and I was like, that doesn't seem right. Something doesn't seem right. Yeah, the minus comes first. What, oh. Yeah. Oh, hey, it worked. Sweet. Wow. I was not expecting it to work, quite frankly. Just real simple, was not expecting it to even work. Like all that explaining and thinking and all of that. Okay, there we go. It's more it's more like it. It's more of what I was expecting. It just doesn't work. It's all that thinking. All that thinking. Nope. Nope. Output 2 3 1 1 3 2. What? You've got to be kidding me. What is going on here? What do you mean? What do you mean? What? 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 I thought I did so well. I thought I did so well. Is this a joke? Oh no, go back. Oh, no, don't lose my code. Oh, no. Uh-oh. 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 Okay. Whew. Whew. Scary. I don't know how that happened. What did we do? What did we just do? Ooh, before we lose this code, man. Oh man. Oh man, scary. Scary. That is just scary. That is just nothing but scary. Downright scary. Oh boy. Oh. Alright, anyway. So, oh. Wait, no, that's wrong. That's not what we want. We want this one. Yeah, this one. It's the one that's giving us a hard time here. So we got two of these open now. Okay. Yeah, you can see. Okay. Oh, wait, what? Wait, now it's correct? Excuse me? Okay, now it's wrong. Alright, let's try that again. Sometimes it's right, and sometimes it's wrong. Oh, it's so funny, because you use random pivots to do this, that's why. So sometimes it's like, oh yeah, good job. And sometimes it's just, nope, incorrect. So sometimes we get the right answer, and sometimes we don't. How you like that? Sometimes right, sometimes wrong. It's good. That's a fun algorithm that can randomly be correct and randomly be wrong. Just depends. So okay, let's study this a little bit more. So what did we get for a result? What happened? Oh boy, this is fun. This is fun. Look at this, man. What is this? 231132. How did that happen? How did that happen? Look at this. This one's fine though. This one's got the right answer. 231213. Yeah, that's what you'd expect. But sometimes no. Sometimes no. Sometimes you get 231132. How did that happen? How did that happen? 231132. Okay. So what should happen initially is what we're expecting to happen is we get this partition should be around 2. So we have 1 1 2 2 3 3, right? That's what we expect for our partition. Then we say we see this 2, we say swap it 2 and 3, right? This 1 gets swapped with this this 1 gets swapped with this 2, and this 3 gets swapped with this 1. So we have 1 2 3 1. That's what we expect after our first iteration. Then we have 2 3. This should get partitioned again into 1 1 2 3. 2 being what we're looking for, right? Our quick select should pick 2. Excuse me. There's no duplicates now, and we could just match these off. We could do 2 3 1 2 1 3, right? 2 goes where the 1 is. Actually, really, that would be it. It was just the 2 and the 1 swap, and you should get 2 3 1 2 1 3. But somehow we get 2 3 1 1 3 2. Now, how does that happen? Can we just print the array at each step? We're so close. We're so close. How does this? Ah, okay. We are so close. So far away. Okay. First things first, oh, fat fingers, fat fingers. All right, we'll do it after the swap and the quick select. We'll see what it looks like, right? So if we do this, the wrong answer, right? One time we get 1 1 2 2 3 3. Then we get 2 3 1 3 2. How does that happen? And then the result, the output, 2 3 1 1 3 2. Now, see, this is wrong, right? And we do it again. Get the right answer, right? 1 1 2 2 3. We should get 2 3 1 1 2 3, right? This is what we're expecting, but half the time we get the wrong thing. So why? Why does this quick select give us the wrong answer? What happened? Well, what's A and what's, I know what B is, right? That's fine. It always should be pointing there, but A. What happened here? What happened here? A is 2, 0, 1, 2, fine. A is 2, 0, 1, 2. But did we just don't get the right quick select here? This 1, 3, 1, 2? Should this not... Is 1, 3, 1, 2 not partition correctly? What do we get for 1, 3, 1, 2? What does that do? Does this sometimes not partition correctly? This 1, 1, 2, 3? You know what I think it is? I think it has to do with... No, this 1, 1, 2, 3 is coming out right every time. It's coming out right every time. Oh. Okay. What's going on here? Does this not do what we think it does? Somehow the pivots are being randomly selected, and oh, that's why. Gotcha. I'm missing something important. Importante. Missing something importante. Importante. Oh, I take it back. No, never mind. It's not the issue. Why? What is going on here? How are we ending up with... Wait, now it's fine? There we go. Yeah, that's what I'm saying. This 1, 3, 1, 2. How does this happen? What is going on here where this occurs? It's so confusing to me. 1, 3, 1, 2. How do you get that? How does that happen? It's got to have something to do with this A and B. Basically picked the wrong pivot, I guess once or twice. And And it's weird because it doesn't seem to happen for 1312. It doesn't seem to happen for 1123. What do we have? What do we have before the quick select? What do we have here? It's so strange. Okay. 2, 3. Oh, it's 1, 2, 3, 1. Oh, that's why. Okay, gotcha. 1, 2, 3, 1. All right. Why does that give you issues? So it's 1, 2, 3, 1 seems to be the one that causes issues. Uh-huh. 2, 3, 1, 3, 3, 1, 2. Yeah. 1, 2, 3, 1, huh. And we don't seem to have issues though here. 1, 1, 2, 3 seems to be consistent. 1, 1, 1, 2, 3, 1, 1, 1, 2, 3. How do we? You know what I think it is? We haven't had this 1, 1, 2, 3. It's pretty consistently 1, 1, 2, 3. I think the issue has something to do with. I think I know what the problem is. I think the issue is because the order statistic that we're looking for, this index, it's a little confusing because that's not the index that we're looking for, right? That's incorrect actually. This is the wrong. It's actually going to be this is the wrong one. This is the wrong thing. It's really confusing because it's actually a plus this new n, where a is 0 initially, but it's here. It's got to be a plus this. Yeah, that's really confusing. I think that's why we're having issues. Yeah, let's see if we run into issues again. Let's do it like 5 times. Yeah, I could explain why, but it's not that complicated. I mean, I should say that. I should say the reason why that was an issue is because we gave it actually an index, and I was thinking, well, it's sort of the ith, it's the ith order statistic. Excuse me, for a given array. But actually, we give it an index within the array, which gets confusing because if we're looking at one segment of the array, then there's a particular index in that array that we're looking for, which is equivalent to an order statistic, but it actually it's equivalent to the ith order statistic only when you're dealing with the whole array. When you're dealing with a fraction of the array, the median for that array would be some number, but you actually would be considering the actual index that you're looking for in the whole array is sort of offset by sort of really that a value. Yeah, it's a little confusing, but that's something I kind of missed when I was programming this. So okay, so it's not that my quicksort doesn't work incorrectly, and the algorithm that I thought of seems to work correctly too. It's really just the that small error, small kind of miscalculation when you're dealing with directly on the array, and you're looking for a particular operating directly on the array, and you're looking for a particular index, and you're using that as sort of an equivalent to the sort of like specifying which order statistic you're looking for. Yeah, I hope that's not too confusing, but I see that. I see that. It really this index should be kind of modified by a kind of automatically, I guess. You know, the index is sort of always greater than or equal to a, basically. Yeah, but I don't know. I'm not gonna change that. I'm gonna just leave it like, you know, as it is. So that way that when you're using this function, one of the reasons why I like to use these internal functions, these like lambdas that are specific only to that function, is exactly for situations like this where it's kind of ambiguous whether or not you should modify this index to add a to it so that way you're always in the range, or just take index as it is, and then when you call it, just make sure in all the calling context you take that into consideration, that you're operating on the entire array. It's confusing because there's sort of like the reason why I like this kind of thing is that questions like this are questions of like generality, in terms of like how well written is your code to handle unknown or future circumstances, right? How well does it generalize to the future, basically, and how well is it written because of that generality? And that's actually something that gets very hairy and very challenging, very difficult, very challenging, and very tricky when you're dealing with software in general. I mean, sort of engineering in general, but because there's a lot of, the more general you generalizable you make something, the more kind of trade-offs you have to make, and the more considerations you have to think about it. It becomes like really complex, really complicated to kind of do things optimally, do things like sort of quote unquote perfectly. And if you're looking to kind of do things as well as you should, it can be way more thinking, way more complicated than is necessary. Whereas if you kind of just like shove your functions inside of the function, the subroutines that you're going to use, then this is the only context they're going to be used in pretty much ever. So you don't need to be so, cerebral about like all of the different trade-offs like you just saw. Like, it's actually confusing if you don't specify the order, if you try to specify the order statistic here as opposed to the index, which is supposed to mean an order statistic. Like, I think if I was going to make this more general, I probably would actually say order, this would be the order, like, or order statistic, and then you'd have to add a to this index before you operate with it, because you're operating on some array, and that order statistic with respect to that subarray, that subsection, is different, right? Like the median order statistic for that subarray might be, the second element in the sorted list. Like, if there's 4 elements, it would be 0, 1, 2, I guess would be the second one, is sort of the one we would be looking for. And if you're dealing with, or not the second element, that'd be the third element, but if we're dealing with, it's a subarray of a much larger array, even though that's the third order statistic, it would be like, if A was 20, it'd be the 23rd order 23rd index in the array that we're operating on, that our algorithm here is sort of referencing, because there is an index that we're referencing each time. So there is an index that we're referencing each time in order to iterate on either the left or right side of the newly partitioned array. So kind of interesting, this stuff. Pretty interesting. And this is pretty involved, this whole thing. This is quite involved. I don't know. I want to submit it to see what happens. I want to do a couple of test cases as well, just to make sure we got, I think we got everything, but just to double check. There are like a bunch of kind of key test cases to look at, and then some other things. I think we got it though. I think we got everything. Okay, good. Don't need to mess around with our invalid test cases. Given array does not have an answer. Nice. I think it's one of these two. One of these two. Up, down. Yeah, this one I think is the one. Doesn't have an answer. Runtime. Nice. Overflow. Okay, which one of these causes overflow? Okay. Just make sure we didn't delete anything that's good here. It's just a copy, so it should be okay. I think it just changed the font. Oh no, I did that. That was me. Made it bigger. So which one of these causes overflow? Probably one of these ones up top. I mean, it's got to be one of the ones we just added, right? Just make sure. I believe so. And it's probably, let's try these ones. Yeah, I was thinking it's one of these. I think these larger ones don't have the same issue. Yeah. So let's say it's probably, it could be, let's try that, just see what happens here. Yeah, these don't even cause problems at all. Really, so one element causes an issue. No kidding, I wasn't expecting that. So now the question is, how far do we get before the runtime error happens? So we get this far. So it happens here. Interesting. Oh yeah, quick select on one, huh? I think this is the one that causes an issue, right? Because we have n is 1, this is 0 plus 1, right? And that doesn't jive. Sanity check. B is less than A, or index is less than 0, or index is less than, or excuse me, index is greater than or equal to nums.size, or A is greater than or equal to nums.size. Nums.begin. I don't know. I don't know what happens when we do this. Excuse me. Still runs into issues. Nice. I don't know if this even matters. Don't know if that even matters. Oh, this probably returns 0 and then this X is, okay. What if, do we need these sanity checks? Okay, yeah. I don't think we do. I don't think we do. Yeah. All this stuff is kind of implicit, I think. Right, X is less than Y, 0, and n minus 1, which is 0, so it just immediately jumps down to begin. But yeah, it doesn't matter. In this case, it didn't matter. So it was this that caused the issue. Yeah, could probably put both of these here. I don't think this should matter either, but we'll just put both of those there. So let's do, yeah, the rest of our test cases. Interesting that our code didn't really handle, oops, I don't want that. Interesting that our program didn't really handle these other cases too well. All right, so now, also I don't think I have, oh I do, oh no, oh sorry about that, excuse me. All right, now what I want to see is, I want to go for it. Yeah, I think we go for it. Ouch. Really? No. Come on. Really? Of all the things. Oh. Man. It's been so much time too. Gotta be kidding me. Of course. Of course I missed something. I was like one of the test cases I could have tested and I just didn't. I was like, I need to test everything, right? Wrong. Why am I getting runtime error on this guy? No. No. That's good. That's very good. Really? Out the gate? Just out the gate. I think, oh man, I'm sad. I'm sad that I got this wrong. I spent so much time trying to get this right, and yet I missed one. Excuse me, one. Where does this happen? Where is the error happening? Huh? Excuse me. Is it here? What is going on? Test. Okay, so we made it through that part. And we didn't make it through here though. Somehow this caused issues. Did we at least get the quick select? Test 2? Did that work? It did. So somehow this caused problems. Test 3. So this iterator, median value, this iterator. What was the iterator pointing to? What? Excuse me? Oh, 4. Oh, 0, 1, 2, 3, 4. Oh, you gotta be kidding me. How's that happen? Brother, what do you mean? Bruff. 5, 6, 4, 5. Okay. Yeah, that makes sense. We swapped. We put 5 and 6 here. We just put the 4 over there, and then, you know, yeah. Okay. So I had the right idea. I'm so disappointed. I had the right algorithm, right idea, but programming it is and was a pain in the neck, and paying the price here. Excuse me. So this index is 4 now. No, shouldn't be. Should be 0, 1. Should be 0, 1, 2, 3. Should really be 3, I believe. And see what n is here. 0. What? Excuse me? No. What? What? Why is n 0? No. N should be 1, 2, 3, 4. And then why is A? Excuse me? What is going on? Hello? A is 4? No, A is not 4. That's not correct. Oh no. Oh no. Oh boy. Oh man. Oh. This is that problem I was describing before. Wow, this is like such a subtle thing. This is the problem I was describing before. I even looked at this too. The problem we were looking at before, where you basically end up moving another element because the thing that you're looking at is sort of you move over, jump over, and you end up pairing off this value with another. Yeah, because you start it, so there's 5 and 5, right? And you move this 5 over to the left side, and you move the 6 where the 5 was. So you have 5, 6, and then 5. Excuse me, but you actually move over again to that. It's the same 5 you just moved. You say, oh, we have to move that 5 to where the other 5 is, really, and then move the other 4. Right? Yeah. And then you don't move it to the, yeah, you move it to, oh, that's funny. Oh, wow. This actually works, but you move the, yeah, you move this, man. Okay. And basically A, you gotta have A is less than B. That's pretty much, I want to say A is less than B. This should fix itself. I don't know if that's totally correct, but it should fix itself here, yeah. That's super confusing. No, it's not B, it's actually X, I think. A is less than X. Is that the one? I don't know if that's the right one. That might be the right one. Oh, that's too much. I probably have to think about that some more. I didn't really think about it too much. I just kind of want to test it and see what happens. Yeah, okay, there you go. The right answers. Yeah, so A being less than X, basically you just don't do that thing that I was describing where you're only checking to see if the value is equal to median value, because you could actually end up jumping into one of the ones that you've already swapped, and then you end up doing more swapping than makes sense. And it gets confusing, and I don't really even know what happens if you do that. So yeah, we'll just go ahead and add that extra condition there. It's probably something else I missed too. There's a good chance, but I would kind of need to go through more test cases to figure out what I did wrong. But supposing that these are not incorrect. What we're doing here. Dude, this is like, it's like a super custom algorithm that's just got a lot of potential flaws or potential mistakes when coding it. Oh, no, man, no, no. Yeah, and I just need to go through a bunch of test cases to figure out all the problems, I think. No. Say it ain't so. Fix one thing, another thing breaks, you know? It's just, I don't know, like this, conceptually, this is just like a very wonky kind of approach, I guess. I think I have the right idea, but it's just very easy to make mistakes, I guess. The thing is, so far, it hasn't been mistakes of the algorithm, it's been mistakes of the implementation. Oh. It's one of those situations where you just randomly get it right and randomly get it wrong. Nice. Nice. Why? Why? Alright. Let's see if this matters, this extra, if it's part of this. There's like a small chance that this is related. In which case I'll be sad. In which case I would be sad. No, it doesn't matter. It has something to do with the pivots. It's too funny. Sometimes we're right, and sometimes we're wrong, you know? Flip a coin. It's good. So why is this happening now? What's going on here? We can kind of get rid of the rest of this stuff here, I think. We don't really need any more. We don't need all this. If we're gonna be this stuck on this question. Oh wow. Oh wow. So output 3. So sometimes we get it right with, well, we should actually take the wrong output. Let's hold on to that. 3 4 1 3 1 3 2 3 2 4 1 3 1. Pretty close to what they got. When it's wrong though, we get 3 3 1 4 1 3 2 3 2 3 1 4 1. Now the whole point of this algorithm is to avoid this situation. Let's go take a look at what happens after the first partition. Oh man. Oh boy. I want to know, is it the algorithm that's wrong, in which case I'll be very sad because I'll have to spend a whole bunch more time figuring out what's wrong with the algorithm, or is it the other thing, which is not just the algorithm, but the how I implemented the algorithm. It could be how I implemented the algorithm. So after the first quick select, we get kind of weird. That doesn't really look right. A whole bunch of ones. I guess it's 3 is what we picked, right? Oh, I think I see the problem. No. What's this median value then? Okay, so one time we randomly select the pivot and everything's basically sorted, and that works. The next time we randomly select the pivot, one, two, three, 1 2 3. The next time we randomly select our pivot, we still get what we want, which is partitioned on the left side and the right side. It doesn't have to be sorted. right? It was just fortunate that it was sorted before, but we get 1, 2, 1, 1, 2, and 3 is the median value. There's nothing on the left side that this shouldn't even enter this loop, right? Nums of x is the median index. Oh, what's the median index here? Oh, that might be why. It shouldn't really matter. Seven, 0, 1, 2, 3, 4, 5, 6, 7. Yeah, I guess it makes sense, right? It should be 1, 2, 3, 4, 5, 6 over here, and then 7 over there. That's fine. So yeah. Everything's to the right is greater than equal. And there's one value to the left that's less than. Now, the thing that's weird here is that you really wouldn't expect this to cause problems. That's the first thing. The second thing is, why would... Yeah, firstly, you wouldn't expect this to cause problems. And secondly, when you partition, how come the duplicate values would be on the right side? Like, there's nothing that says that the duplicate values would necessarily be in this position, by the way. That's actually, I think, something I'm gonna have wrong here, is that I'm assuming that the duplicate values, they just happen to be right next to, when you partition, right next to the 3. I think they don't need to be. No. They absolutely don't need to be. They could be random positions. In which case, this A less than X doesn't really make a lot of sense. We can go back to A less than B, I think. We'll just do that, just to keep things, consistent, copacetic, I guess. Yeah, the 3 doesn't need to be on the left side, by the way. Right, these are all the different sort of random partitions that we can get. Oh man, quite the problem here. Quite the problem we got. No, what's interesting is that even in this case, yes, that's the problem. I understand. So, right, that's actually exactly the issue, is that because we're assuming the largest values are on we're assuming basically this is sorted. The largest values on the right side, and the duplicates are going to be exactly on the left side of the smaller values, which is not the case. So what you've got to do is x is greater than or equal to 0, and what you're looking for is find the next duplicate median value from right to left. So we would say okay. Yeah, we could do this way. Now we say I'm going to do this over and over again. It's really B is the so if nums of B is less than or equal to the median value, keep decrementing B until it's larger. And then you can say find the next duplicate, left to right. Okay, let's see what this looks like. Oops, about to delete everything. Oh boy, right. A little bit more complicated. A little bit more complicated. All right, does this still work? Yeah, it's a little bit better. Let's try, well, we really want to try the other test cases, yeah. I did actually think about this scenario too, and I just forgot to code it correctly. Completely forgot about it. I was just so excited to get something that seems to work. Nice, runtime errors galore. Sweet. Oh, this still gives it, okay. Never mind. Keep running this a few times. So if we get lucky, we get it. If we don't get lucky, then we get a runtime error. Oh. Oh, okay. Actually, I think it's the other test case that caused problems. It's probably this one again. Yeah, it's the okay. So what's the problem exactly? I actually think we don't update this again. Do we have to, I don't know if we update this again. Thinking about it. This doesn't, yeah, this shouldn't be updated. Just by the way. I don't think we even get this far. I think we, it's confusing. Is it? Oh. Oh. Okay. Never mind. What's the problem? Median value 5. Median index 2, and then boom, we have a problem. Median index is 2. Go to 1. B. Where is this issue happening? Boom, 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 boom. Boom, 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 boom. Oh. So it's actually happening somewhere further down here. Yeah, there we go. Something happens in between here. We get issues. Interesting. Oh, we shouldn't update B either, by the way. Forgot about that. It shouldn't really matter, but yeah, B shouldn't really be updating anymore either. Could have missed that. Oh man, this is like this is arduous. This is like so much effort to track down what's wrong. Wrong answer. Wait, what? What? I guess we could leave B where it is then. Wait, what? Oh no, B. No, I'm sorry. B does update after this. I'm sorry, I take that back. B is supposed to update. No, not supposed to do that. Yeah. So this iterator. What is this iterator pointing to? Come on, man. Really? Oh, this is pointing off the edge of the. I think I know. I don't, brother. What is happening? This feels so weird. Like, why are we having these issues? It's 4. Right. 0, 1, 2, 3, 4. Why is that happening? How do you get? Brother, how do you get 4 from this? Excuse me? You gotta be kidding me. You got to be kidding me. Yeah, this is kind of funny. Yeah, I mean, yeah, basically A is 4. Like that's pretty much. And then this ends up in a weird spot. I don't know. It just. You really gotta do A, just nums.size. That seems to be that seems to be causing the issues. Now it's wrong though afterwards. Oh no, please no more. Why these are both wrong now? The second one's fine. But the first one's wrong. So let's get rid of this. Let's get rid of this guy and see what happens. This is kind of annoying. It's kind of annoying. Okay. Median value 3, median index 7. And we end up with stuff all over the place, right? So this doesn't have too much to do with this part. This is just incorrect, right? Sometimes it's incorrect, it seems. Yeah, so zero, 1, 2, 3, 4, 5, 6, 7, right? So there's one value below, which is this one, and it's equal to the median value, which is 3. So we set x appropriately, and b starts off at the end here, and we say if we're less than or equal to the median value, then we would keep moving b. So move b here, should be at 4. And we should end up with 3, 4 over here on the left side, right? We should say swap nums of x with a. Yes. Increment a again. Swap nums of b with a, right? And we should end up with 3, 4 here. And then we should decrement b to this next 4. Decrement x to this next value. We would say if they're not equal, keep decrementing. X should eventually basically go off to -1, really. And similarly, max value larger than the median value from right to left. Oh. Really should be A. Shouldn't even be. Yeah, I gotta kind of fix that a bit. Same thing, A. You don't want to loop all the way over the whole array over and over again, right? It's just kind of inefficient to do that. Okay, so we should get this 3, 4 on the left side. Which I think we do. Actually, that might have been part of the problem, so we're moving too far. Right, because, oh yeah, that should have stopped there. Yeah, oh, that's interesting. Right, we don't want to go back over the, because it really only has to work on one value. Oh, no kidding. Okay, I actually fixed the problem for, okay. Wow. Interesting. So then you get 3, 4 over here, right? 3, 6. That's 5, 6, 7. So this gets mixed with a 4. 3, 4. And now we have the rest of this across should be, I guess, a 4 with a 3. Now I suppose we could do is print each. Oh man, this is crazy. I gotta I have to look at the discussion to see like how this could be done more efficiently, I suppose, like better. But I don't even want to. I just want to like put this to rest. I think I'll make a part 3 where we just go over the solutions. Like this, if I got this in an interview, I would be just done for. Forget it, just absolutely done for. There would be no chance. There would be no chance. This is after the swap, and then this is after the make the partition with the quick select partition. Okay, nice. That's a lot of information. So make the swap, and it looks like this, which is not what I was expecting at all. Why would this happen? What? No, that's not right. Huh? The two swaps happen? No. That's not supposed to happen. That's not correct at all. Why are there 2 swaps? Minus b minus x, and then both of these should just exit. Oh, that's why. It needs to be x greater than a and b greater than a. Oh, you gotta be kidding me. Okay. Wow. Excuse me. Oh, no, that's right. Great. That probably was the problem. Let's try it a few times. 3, 4, 1, 2, 3, 4. 1, 2, 3, 4. Okay. Great. Nice. Okay, let's try. Let's not delete these lines of code just yet. Just comment them out. Man, this is good. This is fun. Wrong? It's very wrong. Indeed, it's wrong. Of course, it's wrong. Why would it be? Of course. Indubitably. Also, we have so much debugging information here. Brother. It's all wrong. It's all so very wrong. Which one of these is wrong, please? Could you tell me? Tell me which one. Would be nice to know. It could be any of these. Let's try the ones at the bottom first. Let's try those ones. There's a good chance those are wrong. I have everything here, so we don't need to, save anything. No kidding. Okay. Hallelujah. 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 Alright, some of these look okay. Which of these are wrong? Two, two, three. Nice. And 1, 2, 3. 1, 2, 3, and 2, 2, 3. Really. Those are the ones that are wrong. You're kidding. You've got to be kidding me. Yeah. Basically, we're expecting the 3 to be in the middle for all of them. That's good. That's good. It's just, why does nothing happen here? Why does this? Okay. Let's print all the debug information. Excuse me. Everything. Let's see it all. Let's see everything. So it just doesn't even touch this, right? Median value is 3, index is 2, 1, 2, 3. Bada bing, bada boom. Bada bing, bada boom. So nothing needs to happen over here, right? This just skips. X is the median index here. Creating on the 0. This basically just goes right down to -1. Skip both of these, which is fine. However, why print it again here? How come this doesn't? Oh, that's why. A and B end up in strange places. That's probably got something to do with it. I think it's because B ends up off the face of the earth here. B doesn't need to be. B really is just num's that size. -1. Should pretty much always be this num's that size. -1 index, and then yeah. And I think n, what does n end up being? I think n is 3. Yeah, this is just to figure out if it's odd or even, right? Yeah, I think that's, yeah. That's kind of funny. But the A, because B is being used here. Yeah. Okay. Alrighty. Nice. So like, it's kind of badly done. I don't know, man. This algorithm, the whole thing is kind of new to me. You know, it's totally new. It's totally like an unusual algorithm. Like everything about it's really weird. Let's just see if things are correct. No. Nice. Which ones are wrong? Are the other ones wrong now, still? Or is now the other ones that were right after making this change, now they're wrong? Oh, these are fine now. Okay, these are all right. All right, but which ones are wrong now? Is it because of what we did? Is it because of what we did? No, that's fine. Which one's wrong? These ones? Maybe these? Please tell me which ones are wrong. Oh wow, where'd that come from? See that? The third one? Really? Okay, yeah. There's just a random 107 million, whatever it is. Yeah, what is going? Yeah, that's supposed to be there. Where did that come from? What is going on? What? What? Okay, yeah, of course. That makes sense. Wow. Okay. Median value 10, index 7, 0, 1, 2, 3, 4, 5, 6, 7. Alright, so there's should be 10 and 15, and then 10 and 13, and then everything else should be basically get partitioned from there. Where do we have all our debug information? It's like every step, yeah. Initially, then we do a swap. We do all of our swaps, and then we print, and then we do a quick select, and then we print again. So we do all our swaps, print it, we partition now, and I think it's 10 again, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 10 elements, should be the fifth one, 0, 1, 2, 3, 4, 5. And now we should exit here and end up down here, and A should be, so we should end up with, now where does this 8 come from? Yeah, 8, oh, wait, 8 and 14, 5 and 6, what is going on here? Hello? Really? That doesn't look right. Again, I think the algorithm, the idea at a high level is correct. The implementation, though, seems to be exceedingly challenging for me to do, to put it together. Yeah, 10 and 7. 10 index is 9. Excuse me. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, that's what I expect. And ten and 15, 10 and 12. After we partition, right, we get this. Or no, this is after the partition, it's this one. Yeah, so now really we should just exit, because where is X and where is A? So X to median index. So this actually should happen before, right? That's probably why. happens here? Yeah, there we go. Now it's correct. Okay. We'll run it a few times. Oh man, I think I need to like, I don't know, like kind of reorganize my thoughts here. Like I think part of the problem is that I have so many different pieces to this going on, and they don't have like I don't have like my thoughts organized very well here. I think that's part of the problem. All right, I feel like I should put in a bunch of random inputs to do more tests. Afraid to. I don't know. I might as well just keep submitting it. It's like, why not? Because that's basically, I need to test it against a test bed of some kind. And really we're testing to see if the implementation is correct, which is kind of bad. Like that's not really what you want to be struggling with, is whether or not your implementation is right. I gotta kind of, yeah, I think organizing my thoughts better is probably part of the issue. Because like, you know, once you've got like a piece of code that's kind of correct, then you can kind of use different parts. You can use it in different places and it kind of means what it should, I guess, something like that. I don't know. There's a lot of moving. There's a lot of pieces I have here too. That's another thing. I just have kind of a lot of things. These kind of subroutines and where these pointers are and all of that. There's just like a lot going on here. Maybe I should try some random inputs, you know. Just a bunch of random stuff. M3, there you go. What else we got here? Does that work? Ray does not have an answer. Nice. Nice. Oh, okay. Too many of these. Need more large numbers. How do we do here? Oh, it's going. Wrong. Oh, that's upsetting. You're kidding. Really? Brother. No. Come on, man. You gotta be kidding me. Is the algorithm wrong after all of that? I'll be so sad. I will be so sad if that's the case. After all of that, the implementation's fine, but the algorithm is wrong. No. Okay, 3, 6, 3, 65, 3. Yeah, kind of bounce up, bounce down. Bouncing all around. Three, 3, 2, 2, right at the end there. You gotta be kidding me. So close. Just swap the 3 and the 2 at the end, you're done, you got it. Oh no, actually it needs to be slightly different. How does this happen? What do you mean? What? Oh, man. Oh, okay. This problem is driving me crazy. crazy. It's driving me up a wall. Oh, no, don't tell me. Don't tell me the algorithm is wrong. No, no, no. I think I know what's wrong, actually. I think I know what I did wrong. Yeah. If a duplicate median exists. If x is greater than 0. Yeah, just throw that in there. This is so complicated. This is like way more complicated than it needs to be. Get this feeling that has something to do with it. No, it shouldn't matter. Doesn't matter in this case. Could matter in the future though. Right, a is always greater than or equal to 0, so. Why? Interesting that didn't make a difference. I guess we'll use the debug output to see what's happening. Yeah, I think it's the implementation again. I don't think it's the algorithm. I think the idea is fine. Oh, there's so many errors though. I don't know. Let's talk about error prone. I don't know how to. I have to like rethink how I'm approaching this to not have so many errors. So many errors. Alright, so we partition once and we see deep breath. Just think about how much time I spent on this. It's like these questions are supposed to be like 5-minute questions. It's not a 5-minute question. Okay. Well, we learned something, right? You learn something when you stretch yourself. So the median value is 3, and the median index is 24. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So literally all the 3s have to be handled. Except for like 2 of them. Okay. So we pair up a whole bunch and then leave a bunch, right? So. Excuse me, I pair up a bunch. Print it. Quick select partition again, print it again. Give us our number. So pair up a bunch. Partition 2, 2, 1, 2. Median value 3. 32, it's way out there. Alright, so we partition pair up a few things and then partition again. And then pick 3 again, median index 32, and pair up a bunch of things again, partition again, right? 1, 2, 2, 2, a bunch of 3s, 4, 20, 5, 4, 5, 4, 4, 4, 4, right? Median value is 2 now. Okay, now the median value has changed. I don't think that's correct. That is most definitely wrong. How did that happen? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. No, that is definitely not the median value at that point. Right. So that's always good. What? Okay. How did that happen? What did we click quick select on? How did we? Oh boy. Oh boy. Okay. Excuse me. N. So N is supposed to be 20. N is supposed to be 20. It's not going to be 20. We know that it's not going to be 20. What's B? That doesn't really matter, right? What A is A, N, A, median index value, median index. Why did this quick select end up where it is? Yeah, we'll just print N and A. We should be able to figure it out from there for with N and A. Why we got 2. 2 is definitely not correct. So 15 elements. So N is 5. No, that's not 5 elements. No, definitely not. It's not 15 elements either here. This is 31. The initial values for N and A. Yeah, so that's oh, that's why. Oh, of course. Oh, duh. Okay, got it. I understand now. See the problem. See the issue. Yeah, the algorithm is still fine, but the implementation is so awkward. Yeah. Okay. Oh boy. Probably can figure out what's wrong and what I'm looking to do to assuage, kind of fix this. Can you see this code? I think so, right? I think it's big enough to see visible. It's fairly visible. So the A value now, yeah, that's the problem. We have where A is now. We really want, there's previous A minus previous A plus 1 is how many values things want to remove. And then set previous A equal to A. Right? Something like this. Now we have the right numbers. Yeah, now we have the right median values. N initially is like 30. Median index is 40. Doesn't seem right. How many numbers do we have? I didn't count. Could throw this at the top here too. It's a good thing we tested this on a big test case. 47, okay, no kidding. Alright. So it takes care of 17 numbers. That doesn't seem right. How do you take care of 17 numbers? Excuse me. I think this is wrong. It's not -1. Yeah, because A is in, yeah, never mind. No, A is already, A already, yeah. Okay, I was gonna say A already has something sort of added onto it, incremented onto it. So let us try again. All right, looks like everything's right with these test cases. Let's go for it. I don't want to look. It's probably wrong. Oh, it's right. Oh, we did it! Finally. Oh man, I'm so sad that we got these wrong. Could have done all this with the more test cases. Oh, dude. Oh, talking about pain. Painful. Not pain, but just not making the cut on this one. Not making the cut. If this was an interview, nope. I mean, again, the algorithm, the idea was correct. The idea was correct. The implementation, on the other hand, not so great. Not so great. Oh, we're pretty good on memory usage. Oh yeah, well that was the idea, so no extra memory. And we're linear. I mean, that was what we're supposed to do, right? Doesn't have to be faster than everyone else's. It's linear with no extra space, constant extra space. We did it. We got there. Now, why is this so slow comparatively? Are you kidding me? Are you kidding me? After all that, it's slower than everybody else's. Is that a joke? Is that a joke? Why? No. Oh, it's funny too. This extra bit at the end is so simple, but this piece in between is like just horrifying. This is like a horrific mess, and then the quick select's pretty simple, and the partition is relatively simple. Like these aren't too bad. These you can kind of come up with on the fly in a few minutes. Shouldn't be terrible. You just have to remember 19937 for your Meissonier twister. Gotta like write that down somewhere. 19937, 19937. If you have to implement a quick select algorithm on the spot. And the partitions, yeah, these you can kind of do in a few minutes. Partition and quick select. However, this whole mess, figuring this out and then coding it on the spot is like nightmarish, I think. I don't think I would ever be able to do that. I don't even know, even after having solved this and having coded this once, I don't even think I could do this again probably in under 30 minutes. I probably couldn't do it again. Like tomorrow, if I had to do it again, under 30 minutes, just code the whole thing again, I'd run into so many issues. I have to figure out like how I can change how this is coded so it's simpler, and then obviously this part's pretty simple. This part's fine, but this is like really the meat of the algorithm. This is like the part that's really meaningful. Got this. Yeah. The thing that's tricky about this is like, excuse me, why is this so slow compared to everybody else's? I get this feeling like there's a really clever way to do this that's super fast and succinct, and everyone else figured it out, but I didn't figure it out, or someone else figured it out, but I didn't. I'm gonna be sad. So I think I'm gonna take a break from this one, end it here. We'll probably make a part 3 where we come back to this problem and do a couple things. One, probably just look at the discussions to see the codes that they wrote, see what algorithms other people came up with. And then also possibly, I think after looking at the discussions, like one idea is like, oh, I can try coding this again, this solution, and make it clean. But I don't think, I'm looking at it, I'm thinking like, I don't think there's a way to really make this clean. I think it's just a messy, I think it's the idea is messy itself. The approach, I think the approach itself is messy. It just is, like it's just what it is messy. I think if I take a look at the discussion and find like a cleaner solution, then I can probably code that up, and then I can keep that in my pocket and remember that for the future. Maybe it would be good to come back and recode quick select, this quick select subroutine, as well as the partition subroutine, and also 19937 Massenet twister, so we can generate random numbers. Yeah, this param type thing also is pretty interesting. This const uniform int distribution param type constructor for our uniform int distribution for our number generating for our random pivots. Yeah, I think that's fine. Come back and come back and code this up again, the quick select and the partition routines with our random number generating, I guess, code, and then or accessing the library, rather, the code to access the library, rewrite all that for practice, and then also look at the discussion. Probably not rewrite this whole routine again, because this is just this whole algorithm again, because this is just really, the whole thing is really messy. Truth be told. I think yeah, I probably would want to take a look at what the discussion says, definitely, and try to figure that out, what they got there, and then once I've figured out what they've got going on there, then try coding that a few times, something like that. That'll probably be like part 3, the follow-up. Call it part 3 follow-up to this question, because this was brutal. This took me so much time. And I still am just so unsatisfied. I still feel like this took forever and not a particularly satisfying solution. Pretty rough approach, rough program, rough algorithm, rough everything about it's rough. I mean, the idea is kind of simple, somewhat simple, like just partition around a median value, an approximate median value, and then pair off the duplicates with larger values until you can guarantee that, and partition again with what's left over until you can guarantee that your partition doesn't have partition around a pivot, by the way, where everything on the left side is smaller, everything on the right side is larger, or less than or equal to and greater than or equal to, until you can guarantee that the left side is strictly less than, and then from there you could pair everything off without very much difficulty. But until you get to that point, that's the meat of that's the crux of that algorithm. What you saw there is that trying to pair off those duplicate values. Yeah, it takes kind of a lot of finagling, because the values on the left side could be in any order that are duplicated with regard to that approximate median, and then the values on the right side are also could be in any order, the ones that are actually larger. And because you could have actually the same duplicates could be on the right side too. So you need a routine to like walk through all of those, find all of those values and pair them off nicely. And then you kind of run into problems because, well, no, it's not. And for some reason this isn't the most efficient, which is really annoying, this whole approach. Like, it's linear time, but I guess, I don't know. I guess because we do all this extra work with this partition again and loop through it again to find the values and all of that, is that I'm thinking the reason why we're not faster than other people is that basically there's some, it's linear, but there's some constant multiple, and that constant's larger than the other routines that other people have. The others probably simpler routines that do, you know, only a few passes rather than doing kind of like a, it's not really clear how many passes we do with this routine, but it's probably a few. It's probably a few through the data. The data. Yeah, my thinking is actually, you probably could do a linear sort, linear sort, an n log n sort with one pass, and then perform a merge routine. I think I've said this before, like basically if you sort it and you take the smaller values, you split it and take the smaller values and the larger values and just kind of pair them up, I think I probably could get like 100% efficiency, something like that. And that would be, it wouldn't be linear time, but it would be faster than everyone else's because n is small enough where even though it's linear, having a multiple constants in front of that O of n for a small number of n, you know, relatively small, even though you're linear, that constant dominates because I guess log, if you take the logarithm of, like, what is it? Was only like 5,000, right? Take log of this over log base 2. 12. It's actually kind of a lot. But I don't know if my constant's more than that. If my constant's like 15 or 20 or 30 or something like that, then we're gonna be a lot slower. Kind of curious to see. I think if I did the sort and merge, I think I'd actually be very efficient. I suspect. It'd be super fast to write the code. It's extremely fast to write the code, I believe. Way faster. So I probably could do that in a couple minutes, or not a couple minutes, but like 10, 15 minutes. Just one sort routine. And then the only real like thinking and coding you need to do after that point would be, I think I'll stay up for like a little while longer, just kind of hang out. I don't think I'll do a stream longer, but the only coding you would need to do after you sort it is basically create a vector and then dump, yeah, just every other value in the vector and then return set the new, you know, set nums equal to that vector. Excuse me, use them like move semantics or use a assignment operator to update nums to that new vector. Excuse me, that's probably the easiest way to do it. And yeah, it's basically one n log n pass and then one linear pass on that. That's it, you're done. That's probably wouldn't be too difficult to do. Probably could do that in 5-10 minutes. But what I have here, oh boy. It's quite the algorithm. It's quite the code. I kind of want to save this somewhere so that we have it because it's so like, it's like, look at this thing, you know, like this is a monstrosity, but it works. That's the thing that's crazy about it. It's like, it's correct. It's monstrous, but it's correct. Yeah, that's something, man. That's pretty wild. Sad that we failed twice trying to put it together. Yeah. You want to go through a lot of tests if you can. It's also interesting because we use a lot of memory just because we have so many of these things, these pointers, and like just all this data that's being used as we go, these integers, it's all this stuff, right? See all these numbers that we use, or these variables that we declare. So actually use quite a bit of memory, even though it's almost no extra memory. It's constant extra memory, but it's like a lot. That's why we're like beat out by a whole bunch of routines, a bunch of other people's solutions. Not to mention, like we declare these things to these objects. Yeah, man, I think that's a good idea. We'll come back. Actually, we'll even do like a few things. We'll like code up the solution that would be like super quick to code, but it wouldn't be linear with O of 1 extra space, We could do that. We could do that. See how fast it takes me to code that. Then we could take a look at the discussion to see what other people did. We probably should save this somewhere. Like I want to save this on my hard disk. I'll do that, and then we hard to save on the hard disk. And we can code up the one that would be quick to code. See how fast it is. Save this to the hard disk. This beast, this animal of a program. Animal of a program. We could practice, right? We could rewrite the partition and quick select routines with the randomization, so we get some more practice doing that. And we can look at the discussions and try to code up one of the discussion solutions, one of the ones that are linear time with constant space, and do that. Try to do that quickly. Do that maybe once or twice. Yeah, those are like some follow-up things we can do to get some practice for a question like this. This is quite the question. I don't know, man. If I saw something similar like this in the future about like an unusual sort of sorting algorithm, I think I would just get destroyed. Like I think questions like this are just really hard. I'm trying to say a little bit less often too, becoming more aware of it. Yeah, yes, quite the 50,000 numbers. Okay, actually 50,000 logarithmically. Log of that divided by log of 2. 15. Yeah, that's interesting. It's still a relatively large constant. 15. If my constant is like 20, then it's going to be slower, right? I don't know what my constant is. How many times do I end up going through this, through this nums array? Seems like a few times. Seems like a bunch. Anyway, yeah, let me go. Give this one a thumbs up. This was an interesting question. This is a tough one. This was like quite the... It's one of those questions that's kind of like as hard as you make it kind of a thing, where the more constraints you put on your solution, the harder it gets to figure it out. But the fewer constraints you put on it, the easier it is. I actually technically don't have O of n worst case time complexity. I have O of n expected time complexity. If I wanted to make the worst case actually O of n, I wouldn't be able to do worst case O of constant extra space, because the quick select algorithm that's guaranteed to be linear time is, not only do you have extra overhead, it actually tends to be slower in practice, but you also have extra memory. You have logarithmic memory, so it's actually it's slower and uses more memory, but guaranteed to be linear. So I actually couldn't do a guaranteed linear with kind of guaranteed lower bound of O of 1 extra space. It is in place. It is O of 1 extra space. However, it's expected time linear. I couldn't do better than that. That's the best I could do. I would like to see the solutions that other folks have. To see. Oh, I'm sorry. I was supposed to. When I was talking, I was looking at this. I didn't show you what I was looking at. I would like to see other people's solutions to see if they were able to get this bound. They probably used a different idea entirely. Although, again, it's kind of beyond me, I would say, at the moment. I would have to really sit and think for a long time to figure out something that's actually hits these bounds with, lower bounds with certainty. So, not just almost certain, but I mean, what do they call that? When it's provable that it's exactly lower bound of O of n time, where we have an almost certain lower bound of O of n time, but not exactly. So let me go. Thank you all for watching, hanging out, saying hello. I do appreciate, or I don't think anyone said hello. So thank you all for hanging out and watch. Thank you all for watching. Yeah, excuse me. Thank you all for watching. Talk to you soon. As I said, I think probably tomorrow I might take a look at this and think about how I could. Yeah, we'll do that follow up, which was look at. We'll code up a fast solution to this, or a solution that can be coded up quickly. We'll do that. That's one thing we'll do. We'll look at the discussion to see what other people did, so we can try coding that up. We can code up our quick select and partition routines again, and also code up the randomization, right? So we can get more familiar with, like, oh, if you were in an interview and you had to code up a quick select routine or a partition routine for a quick select, could you do that in a few minutes? Practice that, and then I want to save this beast of a program that we've got written here, because this is a lot of fun, and I don't know, it's something about it. I want to hold on to it. I don't want to lose it in cyberspace here. Save it to my hard disk. So yeah, we'll do those things tomorrow as a follow-up. Do a part 3 follow-up. It's quite the doozy, this question. There's a lot of stuff that was involved and covered. Got in a little bit into randomness too. Randomness is there's some follow-up questions too with regard to like randomness, which is just plain old, like, if you had to implement a uniform integer distribution where basically your function would return some integer between two values inclusive, where those values have an equal probability of appearing, right? How would you code that? Right? That's sort of a follow-up question. This if we're talking about randomization and quick select and all of that, because that's a question you might get in an interview. I know some people have, and that's a good one. That's one that I really don't have a clean answer to either. Like, it's something I have to review. I don't think I've ever really had like a good answer to that. So yeah, that's probably part of the follow-up. We could throw that in there too in the follow-up. Try to figure out a reasonable answer to that question. So yeah, let me go. Thank you all for watching. Talk to you soon. Have a good rest of your night.